Good evening, students. Welcome to VV Live. Very good evening. Welcome to Unacademy VV Live. Right? Can see here. Recently it is started. EAMCET Rankers batch recently it is started. That is on 24th of December. It means yesterday only. Just a day before. Just yesterday only. One day before it is started. If you are an aspirant of EAMCET, you please join and use this code VVLIVE, right? And also should get a plus subscription. You are going to get all these benefits like a premium content at affordable price, structured live classes, live courses, and dedicated live doubt clearing sessions. Regularly quizzes will be conducted for self-analysis, and for complete preparation many batches are going to start and already started, and daily practice papers, full length mocks, okay, with a detailed analysis you are going to give with a single subscription. If you are using for this code VV Live, you are going to get discount, a good discount. And also, students, you see here, Unacademy is providing 20 plus top educators, 10 plus batches, and also 250 plus courses. Apart from that, so you see here 2000 plus lessons. It's not a simple thing, students, and many more. Okay, every day it's going to add. So for that all, okay, to get subscription, I request and I suggest you to use this VV Live, right? And now for today's discussion, okay, for today what we have to discuss? We have to discuss about semiconductors, right? Semiconductor devices or semiconductors also we can say, okay, like this, semiconductor devices. You see, students, semiconductor, conductor or insulator, this is the classification of solids. Based on its electrical properties, we are classifying the solids. Solids are of two kinds: crystalline solids, right, and sorry, we have amorphous solids, amorphous solids we have. Like this, solids can be divided based on what? Based on periodicity of arrangement of atoms. If atoms or molecules are arranged, okay, with a periodicity, that is said to be crystalline structure, right? That is said to be crystalline structure, this one. And if periodicity is missing randomly, okay, right? Like in rubber, right? Okay, if molecules or atoms are arranged, that is said to be amorphous solid structure, right? For crystals, what we can say? Quartz, right? Metals, usually metals, are belongs to crystalline solids. Now in this, you see, these crystalline structures can be classified based on electrical properties into three. Because, students, we are going to discuss about semiconductors. So semiconductors, for that we have to discuss. So classification is must and should. So therefore, these crystals are classified based on electrical properties into three groups, right? What are those? Those are nothing but conductors, right? Conductors. Next one is, right, insulators. Next one is insulators. And the third case is semiconductors. Right? You see, based on electrical properties, like that we are saying. Electrical properties, in what way we have to understand? Based on the passage of current and the resistance offered by the material, resistivity, conductivity, and all these. These are the electrical properties what actually we have in case of conductors. Now you see, suppose conductors means generally metals are the examples. All the metals are belongs to conductors. You should know this point, right? Now in this case of conductors, electricity means current is able to pass easily as compared to these insulators. As compared to insulators, in conductors easily current is able to pass. Current is nothing but charge of rate of charge of electrons, means a flow of electrons, in simply if I say. So electrons flow is there in conductors easily as compared to insulators. If I say about semiconductors, in between conductors and insulators, properties will lie for these semiconductors. And one more, if I want to discuss in case of conductors as in insulators or semiconductors, in terms of energy gap, energy bands, we can understood for this. Say here, so like this, okay, like this and like this, energy bands I am calling for this. See, this is of valence band. This is of conduction band. So actually here these lines are not required, right? These lines are not required. 1 second, just a second, right? 1 second. I'll draw for this one more time, right? So like this. This is the, okay, this one is the energy gap related to valence electrons. So that is the reason why I can call this as valence band energy. This energy band is said to be valence band. Whereas conduction band, from valence band into conduction band, when electrons are jumping, usually electrons are in its valence band. As you know, students, surrounding to the nucleus, this is the nucleus, protons and neutrons are present. Okay, electrons are revolving in its stationary orbits, we know, right? If you consider this as the radius of an atom, right? Now, what I am going to say is, these electrons, whatever the electrons are revolving, outermost orbit electrons are said to be, these are said to be valence electrons. So, corresponding energy band is valence band energy. Now, whenever these electrons are jumping from valence band to conduction band, these are the electrons which are present in valence band initially. Now these must jump from valence band to conduction band, then and then only electricity is possible. This point you should know. When this current or electricity is possible, electricity means current here. Current is able to pass. Whenever the electrons which are present in the valence band are jumping from this band to the conduction band, okay, this is imaginary completely, conduction band, then here in this band electricity is possible, means current is able to pass. So students, be careful here. What I am saying is, okay, the gap between these two, valence band and conduction band, the gap if it is less, easily these electrons can jump and electricity is possible, okay, quickly. So therefore, depends on this energy gap, we can classify for these three, right? So 1, 2, 3 depends on the gap. Suppose, for example, you see here, we'll take one diagram. So here is the valence, okay, 1 second. Here is the valence band. What I am saying, this is valence band. Now this is nothing but conduction band, like this conduction band is there. Try to differentiate this one. Here up to here valence band, like this, you see here, like this. This is valence band. Now this part goes to conduction band, like this. This part goes to conduction band. Now you see the combined section, combined region is there, no? So you see, you can say like this one and this one, you see. Means I can say this valence band and this conduction bands are overlapped. What I can say? These are overlapped. So this happens in case of conductors, students. This happens in case of conductors. That means already this VB and CB are overlapped. That is the reason why easily, even at the room temperature, that is at 27 degrees centigrades, electricity is possible with the metals, or I can say as conductors. So energy gap is 0, I can say here. Whereas in case of semiconductors, let me come, means say obviously insulators means it should be very far, means that the gap must be very far. In case of semiconductors, what happens, you see, this is of valence band, and now this is of conduction band, this is of conduction band. Usually in the order of 1 electron volt, this energy gap will be in the order of 1 electron volt. Here like this, right? Here like this, you can see valence band, means from here to here electrons can jump. Suppose in case of silicon and germanium, In case of silicon, it's of a point, 1 second, it's of 1.21. It's of 1.21 electron volts, 1.12, no, not a 21, 1.12. 1 second. Okay, right. 1.12 electron volts, and here it's of, sorry, this is of 1.21 only, not 1. I'm really sorry for this, and 1.21 electron volts, right? 1.21, and for this 0.75 electron volts. Anyhow, this is close to 1 electron volt. Be remember for this. Whereas greater than these values comes under insulators. Greater than those values comes under insulators. So for semiconductors, in between conductors and insulators. So likewise, here I can say here our discussion is about semiconductors. This semiconductors electrical properties lies in between insulators and conductors. We remember, like here properties will be there generally: current, what we call current, next resistance, next conductivity, resistivity, right? Conductivity, right? This is the next resistivity. All these are the properties, electrical properties. So these are the different properties, varies from one to another in these three kinds. In these three kinds, it differs. Now you see what is more about conductor and semiconductor. I can give one differentiation here in between these two. In case of conductors are nothing but all the metals. You remember, basically these are metals. In these metals, what happens? Here it here these obeys Ohm's law. Ohm's law will be valid or obeyed in these conductors. Ohm's law means what? We have like V is equals to IR. So suppose voltage is shown here, resistance is current is shown. Sorry, current is shown here. So the graph comes like this, straight line. Graph comes a straight line. I by V means 1 by R. Here the slope becomes delta I by delta V. Na? So this is nothing but I by V is nothing but 1 by R. Okay. Suppose if you are taking voltage here, current here, resistance you are going to get. So what I can say, this is a constant. This value is constant. So as current, strength of the current is directly proportional to the potential difference. Okay, in case of Ohm's law, in case of metals, this is obeying Ohm's law. What we can say is the strength of the current, Ohm told in his law, at a constant temperature. Okay, Ohm's law is given like this: at constant temperature, the strength of the current is directly proportional to the voltage, right? So I is equals to, one proportional symbol, if you take out one constant, we should take 1 by R into V. So this is known as V is equals to IR. Famously we are calling this as V is equals to IR. This is called Ohm's law, students. This is called Ohm's law, right? Now in case of semiconductors, whether it is straight line or another way it is resulting, for that we have to discuss, right? Hope you understood for this. In case of semiconductors, definitely it's not like that. Definitely it is not like that. It will be like this. Before all I am showing for you, it will be like this. So like this and like this. Here biasing conditions will be there, right? Here voltage and here current is shown, right? In this direction milliamperes range, in this direction microamperes. In this direction is the reverse bias condition. This is forward bias condition. Anyhow, we are going to discuss right, this one also. Likewise, here we have now coming to semiconductors. Students, you see classification of semiconductors. Coming to classification of semiconductors. Here I can say in two ways it can be classified. One is intrinsic semiconductor. One is said to be intrinsic semiconductor. Second one is extrinsic semiconductor, students. What is intrinsic semiconductor, students? Be remember, this is a pure semiconductor. Examples are nothing but silicon and germanium. Be remember these two. Extrinsic semiconductors, these are nothing but doped semiconductors. Be remember, or I can say impure semiconductor, or I can say impure semiconductor. You can call this as impure semiconductors also, right? So for this mixer means this actually what is doping and what is extrinsic semiconductor. Now we will continue below, right? Now intrinsic semiconductors are nothing but pure semiconductor, students. Nothing is there to discuss much about this. Examples are germanium and silicon, and what you have to know is these are tetravalent atoms. One thing you should know, these are tetravalent atoms. These are tetravalent atoms, which means valence electrons number is 4. In outermost orbit, how many electrons are there? 4 electrons are there. So that's the reason why these are called tetravalent, valence electrons number, right? It's nothing but 4. This point you should know. These are the intrinsic semiconductor. This is semiconductor means this only, intrinsic semiconductor means this one, right? Semiconductor means pure. If they, until and they are mentioning it as extrinsic, this semiconductor means pure semiconductor only. That means intrinsic semiconductor only. Now here it's very clearly shown on other side. Doped semiconductor, extrinsic means doped, or I can say impure semiconductor, means something is going to be adding to the pure semiconductor. This point you should know. To the pure semiconductor, something, some atom, other atoms, foreign atoms are going to be added. That process is called doping. That process is called doping. Doping means what, students? Here you see, doping, right? It means, right? It means adding of impurities. It means adding of okay, impurities. Impurities means foreign atoms, other atoms, right? Don't think in another way. Impurity means other atoms, except these intrinsic semiconductor atoms. Adding of impurities is called doping. The process of adding of adding of impurities is called doping. That's it. Now you see here, in case of tetravalent atoms, say here is the silicon. Silicon is shown here. This case, what we can say here, 4 are the valence electrons, like this, and like this. Valence electrons for showing valence electrons. Okay, I'm giving this kind of right a picture. Now here 1, 2, 3, 4. In silicon, 4 valence electrons are there. Suppose, students, if you are going to add for, okay, pentavalent atoms and tetravalent atoms. So what is going to happen? For that we have to see. Penta means, students, you remember, it's number 5. So not tetra, trivalent. This is of trivalent, not this one. 1 second. This is of tetravalent. This is of trivalent. What I have to say? Tri means 3. 3 valent atoms. So 3. So in one case 5 valence, in another case 3 valence electrons. If you are adding for this, what happens? We will see. In case of pentavalent atoms first. Now what you are going to do? You are going to add for 5 valence electrons. 1, 2, 3, 4. Now with the 4 tetravalent, these 4 of the pentavalent atom pentavalent atom electrons gets involved in covalent bond. Now the covalent bond is formed, but one excess is there. This one excess is then a pentavalent of 5. So this is number 1, 2, 3, 4 and 5. So here this electron is excess. This electron is excess. Okay. So excess number of electrons means negative charge it can contribute. So that's why the forming semiconductor is said to be N-type semiconductor. We remember the forming newly formed. So Newly formed semiconductor is N-type semiconductor, students. Hope you understood for this. Means in this kind of adding doping, should not call this as adding, doping process. Now here what is going to be forming N-type semiconductor? What is N-type semiconductor? A semiconductor which is having excess number of electrons in it by adding, adding pentavalent impurities to the intrinsic semiconductor, that is silicon. We are going to get for this N-type semiconductor. Hope you understood for these students. Very simple. Initially tetravalent atom we are choosing, that is nothing but pure semiconductor, or I can say that as intrinsic semiconductor. It has 4 electrons in it, 1, 2, 3, 4 in it, already it is there. And now we are going to bring one foreign atom, another atom, whose valence electrons number is 5, which is called pentavalent, right? For that, phosphorus, phosphorus, next bismuth, like this we can take arsenic. These are the pentavalent atom, students. So such atoms, if you are going to add for this intrinsic semiconductor like silicon and germanium, what happens? One electrons will be left free. So this can contribute current now. This electron can contribute current. So excess number of electrons here, remaining all are in covalent bonds. Remaining all electrons are in covalent bonds except this one. So this is free now. Now this free electron can constitute current. So basically charge is negative, electron charge is negative. So electrons number is excess here. So newly formed semiconductor is said to be N-type semiconductor. So here 2-3 points you have to question yourself. In case of N-type semiconductor, what are the majority charge carriers? Majority charge carriers are nothing but electrons. In case of N-type semiconductors, which charge is more? Negative charge is more, right? To form N-type semiconductor, what kind of atoms we are going to add? Pentavalent atoms we are going to add. What are the examples for this? Like phosphorus, arsenic, right? Like this, these are the valence, these pentavalent atoms. These 2-3 points you should remember. Next, coming to another kind of extrinsic semiconductor. One semiconductor we are discussed in this extrinsic. So here again extrinsic is of N-type semiconductor. I am writing now here, you see. Here this is of P-type semiconductor. Now for one kind we are discussed. N-type semiconductor is over. Next, P-type semiconductor, when it forms. Here only we are already discussed, students, trivalent. For this intrinsic semiconductor like silicon and germanium, if you are going to add for this trivalent atom, what is the newly formed semiconductor? For that we will see. Say this is silicon again. Now here it is having 4. Right. Let me take once this diagram like this. Now the silicon is having 4 valence electrons, which we are showing in this way, in this diagram. And now suppose trivalent atoms we are adding. Tri means 3, na? So 1, 2, 3. Students, here you see 1 is left free. Means here there is a lagging. So lack of electron. What I can say? Lack of electron, which is called a hole, students. This hole can carry a positive charge. Hole behaves like a positive charge. So lack of electron in covalent bond is said to be hole. Students, remember, hole means lack of electron in covalent bond is hole. Now this hole can behave like a positive charge carrier. Remember, it cannot travel through the wires, through the metal wires. It cannot travel. Remember, it can travel only. It can carry charge only in the bonding, covalent bonding. Means I can say it is present only in the semiconductor material itself. So now here if you observe carefully, what happens you see, what are the observations we can. So whenever this hole is going to present, I can say here charge carrier is hole, here charge carrier is hole. Next, and here this is carrying a positive charge, this is carrying a positive charge, and next, right, here it is carrying a positive charge, right, and here majority charge carriers are nothing but holes in this kind of semiconductor material. Majority charge carriers are holes only. What are the majority charge carriers in case of n-type semiconductor? Electrons. Here this is said to be p-type semiconductor, students. Why it is p-type semiconductor? It is carrying positive charge. It is carrying positive charge. So that is the reason why p-type semiconductor. So positive charge is majority here. That is the reason why it is called p-type semiconductor, students. Right? So likewise here, what we concluded here, whenever trivalent impurities are added, students, examples for this, aluminum, right, beryllium, boron, aluminum, gallium, these are the examples for trivalent atoms. These are the examples for trivalent atoms. So here, due to positive charge as majority, these are said to be p-type semiconductor materials, right? Examples are given, right? Majority charge carriers in p-type semiconductors are nothing but holes. Holes are the majority charge carriers. We remember. So likewise, with examples you should know. Here one point I will remind. Majority charge carriers in p-type semiconductors are holes. Majority charge carriers in n-type semiconductors are electrons. It doesn't mean that the absence of holes and here holes and here electrons. Electrons and holes pair is there. Electron and hole pair is there. Okay, that is in the covalent. You see here it is the electron. This is the hole. But majority, for majority, if you are asking, you can say in this way. In case of p-type semiconductors, positive charge is more. Be remember, for that trivalent atom is to be doped with the intrinsic semiconductor, whereas in case of n-type semiconductor, pentavalent atoms are to be doped with the intrinsic semiconductor. Then n-type semiconductor is going to be forming. Like this, we have classification, friends, and with examples you should remember for all of this. So like this, and now here title is given like this. In what way we are taking the title? Semiconductor devices. Semiconductor devices. You see, what are the semiconductor devices we have? For that, if you are asking, I can say we have like a PN junction diode, friends. Here it is of a PN junction diode. You see here, PN junction diode. Junction diode. This is one device. And next, transistors. Transistors. Next, rectifiers. Rectifiers. Okay. Next, logic gates. Logical gates. These are all the semiconductor devices, students. Be remember. Means these all the devices are made from semiconductor materials, either with intrinsic or extrinsic semiconductor. Generally, silicon and germanium, are used to prepare these all the devices, semiconductor devices. Now, actually, we have to discuss one by one of all this. Now, for today, I am going to define for this PN junction diode, because time may not permit for the discussion of all this. So, PN junction diode, PN junction diode. You see, students, here P means p-type material, N means n-type material. Junction diode. Here you see, this is also called as simply PN diode. You see, this is also called as PN diode. Sometimes we can say this as diode also. You should remember one point here. Di means two. Di means two. Ode relates to electrodes. This ode relates to electrodes. Electrodes. So means two electrodes, two electrodes device is this one. PN junction diode is nothing but two electrodes divides. Two electrodes means in what way you have to realize still. Say here this of P type material, this of N type material. Suitably when we join these two. So this side one terminal goes and this side one terminal goes, students. Now this is the one electrode, this is another electrode. So now it became two now. So P type material and N type materials are joined suitably. Suitably if you are joining, one junction will be formed here, and from that we are going to discuss about PN junction diode. Okay, for today, okay, I'm stopping for this point at this point, and you just see the things what actually we discussed from the beginning. If from here onwards, in the next class I will continue. Just give a glance and you have to okay, revise once what we have discussed. Recap, it's nothing but one recap, right? Like this. Students, hope you are all understanding what I am explaining here. It's very simple and interesting one. And if you are not yet subscribed students, okay, for a plus subscription, you better to choose. In India, this is the best platform to learn, to gain the knowledge, to learn the subjects and to gain the knowledge. This is the best platform, 100% I am sure. And this also for this also you can see the recent batch. Okay, thank you for listening, and we'll meet in the next class, right?